Thank you so much. I think I control over here, yeah? Well, it's an honor to be here. Thank you for showing up and being here for this afternoon. I want to show quickly our team. You just heard about us looking at floods and wildfires and hurricane impacts. This is the team that does it, and these are the folks who've produced many of the techniques that I'll show, some of the data, and a lot of the science that's being done by our teams. These folks work on hurricanes on the East Coast, on barrier islands. They're characterizing coastal change in Alaska. We're going to have a big product on that in the coming months, something to look forward to. But these are your federal civil servants who are working hard on these things. So coastal landscapes. I feel very fortunate to be a Californian. I'm a fifth generation Californian, and my family has always enjoyed the coast. I've always lived by the coast. I've always gone to the coast, and I've always been intrigued and loved coastal landscapes. And so when I was a kid, it was more like exploration and discovery. You know, what's under this rock? Oh my gosh, look at this puddle. What's that creature? Or what's around the point there? Let's go check that out, you know? And then as I got older, it was more like, why are all these rocks here? Why is that cliff so steep? Is it safe to sit under this cliff? Check out the sand. Where did the sand come from? That wasn't here yesterday. Is that coming or going? Or where is it going to be tomorrow? And those questions led to a whole career, and it's why I'm here today. And so I'm a geomorphologist. I study these landscapes, and I feel very fortunate to be able to study such wonderful places. And one of the reasons our coastal landscapes are so unique is because they're shaped by waves. Tides and winds and things, but primarily waves, right? The waves are battering the coast, and that's somewhat unique in geomorphology because all my colleagues who work up in the landscape generally think about vertical forces. They think about gravity pulling things down or rainfall raining down on the landscape, and that's shaping the landscape. On the coast, we have a forcing coming from the side, right? These waves, it's a beautiful photo by Woody Woodworth of Ventura. These waves are coming in battering the coast, right? Up the coast, it may be battering, cliffs and steep landscapes, whereas down here, closer to us, it's moving sediment along shore. And so that's sort of a very unique setting on Earth, and it's why we have such a unique coast. And on the rocky portions of our coast, these landscapes are truly, truly unique. And I like to say they're wonderfully complex. And you would know this is wonderfully complex because this is down by San Simeon. Think about trying to walk across this landscape, right? It's, oh my gosh, I'm going to have to go over here and over there, and if I want to get over there, it's like you maybe have to backtrack. And that's because there's all these nooks and crannies. There's all these little holes, big holes, moderate-sized holes. And those are a function of the fact that the geology underneath it, the rocks, are being weathered by these waves and resulting in these complex landscapes. Now, these rocky coastal landscapes are some of the most complex on Earth. So what I mean by that is they have all these undulations and of different sizes and scales that are really, really complex. Again, some of the most complex landscapes on Earth. They're not flat prairies, right? These are really interesting landscapes. And one way to measure that is to think about what we think of as rugosity, and that is sort of how rough this is. And so you can think about taking maybe a yard of fabric, a square yard of fabric, and if we laid it out over a flat grassland, you wouldn't need any extra material to make that square yard cover a square yard. But if you did that here and you really tucked it in all these little nooks and crannies and stuff, you need a lot more material to cover a square yard, right? Maybe 2-3 times as much material to cover all that. And so that sort of helps maybe you understand how complex these landscapes are. There's a lot of nooks and crannies and curvature to them. And so mathematically, if you're into math, we think of these landscapes as being fractal or fractal-like. Does anyone know what a fractal is? Yay! Awesome. So fractals are these cool patterns that exist mathematically, but they're also, we see them a lot in nature. And often we see them as having repeating patterns at different scales. And so, for example, up there in the upper right, you can see that really neat sort of pattern. Well, if you look at that big object in the middle and then look at the very top of it, it's just repeating itself, and it's repeating itself over and over and over again. And so a true fractal will do that to infinity. Coastal landscapes don't do that to infinity, but they go pretty darn far. And so if you look on the bottom left, there's that really neat sort of fractal pattern. Well, that pattern looks very similar to maybe what a rock in the intertidal may look like if you looked at it in profile. It also looks very similar to a shoreline if you were looking down at a rocky shoreline from space and trying to map it out. Those things are very fractal. In fact, if you read a book or any article about fractals, they'll probably ask you the question is asked often, how long is the coast of England? And those who know fractals know the answer is what? It depends. Yeah, it depends. There's no answer to that question. It depends on how long your ruler is. Now that's weird, but we can talk afterward if you want to talk more about it, but that's what a fractal is. Fractals are really complex, and they provide these really interesting patterns. Now, why that should be interesting to you is because it's good for you. It's good for your brain to look at fractals and understand them. And so there's a whole literature on this. So whether it's a tree or a coastal landscape or a piece of broccoli, your brain enjoys studying and looking at these objects. And so much so that there's a whole literature, a lot of folks who are architects and do urban planning who are trying to introduce these fractal patterns, these natural patterns to urban landscapes, just for the well-being of you and me, okay? So one of the things I do is I'm very fortunate because I live in Santa Cruz and my office is near the far west side, and so sometimes at lunch I get to go out here and look at fractal patterns and let my mind sort of relax. And so I want to encourage you all to do the same. Get your vitamin C, SEA, every day. Your brain truly does enjoy this stuff. It's good for you to look at these things. It doesn't have to be this. It can be a tree too, but know that these coastal landscapes are something your brain enjoys to look at and digest, and try to do it as much as possible. Fractal landscapes on rocky shorelines are also really interesting and valuable for our ecology. Now, I'm not an ecologist, but those who are tell me that complex habitats, so rocky settings that have lots of nooks and crannies that are really fractal-like, have a lot more species in them. And that kind of makes sense, right? The more nooks and crannies and the more diversity in them, the more species you should see there. And then the total abundance of animals, how many animals is directly dependent on how much area they can sort of sit on. That whole idea of taking that piece of cloth and trying to squeeze it in all the nooks and crannies, how much area is there for them to live upon? So it's also interesting to think about how these complex settings are valuable for the ecology and for the animals that live out there. Okay, so that's number one. I wanted to just touch upon sort of how beautiful and interesting the coastal landscape is. And I also wanted to focus on this, number two, is that it's always changing. So I was fortunate enough last year to be in Western Australia, at the University of Western Australia for the summer. And this is taken on that western coast of Australia. Brilliant sunsets, a beautiful place. One of the things I want to impress upon you in this photo is that area of the surf zone. And right, when we were kids, we used to go down there and just stand, and as the waves washed up and down, you'd slowly get buried by the sand, right? And that's because the sand's being carried by each wave, and no matter how small the waves are. And so one of the things I like to think about is that even when I'm sleeping, the ocean is changing my laboratory, right? My laboratory never stops changing the place I study, which is the coast, because there's always these forces working on it, moving materials, moving sand. And as an example of this, let's just say you walked out to the beach and you saw, oh, my perfect shell, I need to get that shell. Well, if you were up on the hills and you found that shell, you might put a little flag on it and say, oh, I'll come back tomorrow and pick it up because I'm too busy to pick it up today. But if you were on the beach, would you do that? Would you put a little, no, you wouldn't, right? You're like, that's kind of silly, right? You know that that shell would be, who knows where the next day, right? So just to help you think about the fact that these sand grains and the shells and the rocks are moving all the time out there. We're always reshaping this coastline. Sometimes it happens on sort of small scales like that, and sometimes we see fairly large movement of sediment. This is after some winter storms in 2016 near Moss Landing. You can see all the scarping of the sand dunes. The sand dunes extended far beyond where that person is walking before this event. And so sometimes we see some fairly large movement of sediment. And I'll talk about that a little bit more here in a second. And our cliff coasts, although we tend to think of these being somewhat, permanent or, you come back to this setting and it looks the same year after year after year, these settings are changing too. In fact, if you were to look to the right where I took this photo, you will see all this loose rock down here I've placed in this red circle, right? And this is because that cliff face is sort of slowly raining down rocks all the time. And so these cliffs are changing over time. And so these are on order of, centimeters maybe. And on average in the region we see something like 6 to 12 inches of erosion of our cliffs every year. Some of that's due to these slow raining of rocks off the cliff face, and some of that's due to larger scale events, landslides and rock falls and the such. And some of those events are fairly huge, right? This is Mud Creek from a number of years ago. This was a few days after that landslide occurred down in Big Sur. California gained 12 or 13 acres in a few minutes. And then the ocean started working at it, and I'll show you some results from that in a little bit. Obviously, this destroyed Highway 1. The highway was closed for a little over a year, I think, that one. And again, I'll show some more data. So lots of different scales of changes from, rock falls, sand grain movement, to large-scale landslides and erosion events. So one of the neat things of being at the U.S. Geological Survey is that we, as an agency, our motto is science for a changing world. And so the coast, of course, is one of those places that is changing all the time. And so we have a small group that's spread along our three main coasts, Pacific, Atlantic, and Gulf Coast, who are studying and providing the nation data about the rates of change and the reasons for the change along the coast. And so I want to transition a little bit and show you just some of the new types of things that we're doing, some of the new types of data we have. They're also your data, because a lot of these databases are public facing, and I'll show you some of that as we're going along. And so we're really in a neat era. You think about 20, 30 years ago, we were still doing a lot of work using some older surveying techniques, or using aerial photos that were only taken every couple years or something. And now we really have moved in the last decade especially into this big data era for coastal change studies. And it's really exciting, and I want to just highlight a few things that we have available to us to help us measure, understand, and forecast change. And I'll walk through these sort of from the top to the bottom. We have brand new techniques using satellites, which are kind of exciting. We have some aerial surveying techniques that are really fun, and we're leading here in Santa Cruz. And then we continue to be on the ground and on vessels on the water to survey coastal changes. And I'll show you a couple examples of that too. So what can we see from satellites? This is one of the Landsat. This is an artist's impression of one of the Landsat satellites. And one would think, gosh, satellites shouldn't be that useful to understanding coastal change, but it turns out they can be extremely useful, and we've only really discovered this in the last 5 to 10 years. And since about 2019, we've seen an explosion of use of satellites to observing coastal changes. If you're interested in this, I would highly recommend you looking at the CoastSat website. I'm sorry I don't have a URL or a QR code, but if you're interested in data like these, and I'll explain these in a second, go to CoastSat. That work was partially funded by the USGS with our partners in Australia. And so what I'm showing here is changes in the beach near Moss Landing. So this is the beach just north of the harbor entrance. And so the wonderful thing about satellites is that we have Landsat records that go way back into the mid-1980s, and we can use all that information to track coastal changes over time. Excuse me. Wow, sorry, I'm a little dry. Is there any water around? No? Oh, there is. I hate to use a plastic bottle, especially in front of this crowd. You didn't see that? Sorry about that. So what you're looking at here are shoreline positions over time. And what's really kind of neat is it kind of looks like a heartbeat in some ways, right? You see it goes up and down and up and down. And so up is a wider beach and down is a narrow beach. And so what you're seeing in that heartbeat is that annual cycle of erosion and accretion, of beach widening and narrowing. So generally it's wider in the summer, and in the winter it's much more narrow. And then you can also see some of these other interesting sort of longer term waveforms in there. For example, in 2014 or so, we saw a number of years where the beach was much wider than it was previously or since then. And so some really fantastic patterns in the data we can get from satellites. And one example that we published a number of years ago was the effects of the Soberanus wildfire, who some of you remember, in Big Sur. It burned like 2/3 of the Big Sur River watershed and lands outside of the Big Sur watershed. And then that winter we had some traumatic rainfall. We had really high rainfall in 2017. And what that did is it washed a tremendous amount of soil off the landscape, and the sand in that soil flushed into the Big Sur River, buried a lot of the lower watershed, and was washed to sea. And what we saw down at the mouth of the Big Sur River at Andrew Malera State Park was a broadening of that beach and then movement of that sand down coast. So we can use these data from satellites to actually track those pulses of sediment that enter from the landscape and as they move down coast. And if you're interested in that, I could talk about that for an hour, but I have no time to do so. But come see me if you're interested in that or the implications of that. Another interesting use of these type of data was done up in the Klamath. So now we're sort of far north of Monterey Bay, up near the northern extent of California. But what's really interesting up there is that using the same 40 years of data, I'm showing there on the right-hand side a sort of this, what I call the blue blob, okay? The blue blob is a map of the beach width with time. And so as you can see, shoreline change at the top. If it's sort of in the warmer colors, it's erosion. Bluer colors, it's accretion. And you can see, starting up near the Klamath River mouth in the late 1980s, this blue comes in and then spreads down to Gold Bluffs Beach, right? That's about 100 meters or more of beach widening at Gold Bluffs Beach. Has anyone been to Gold Bluffs Beach? Yes. It's a fantastic place, isn't it? Super broad. The elk come there, right? It's fantastic habitat. If I told you that beach didn't exist 150 years ago, would you believe me? You wouldn't, because it's so wide. Well, it's true, it didn't exist. And so the earliest records and our Native American partners up there described this beach as not having a beach. It was truly a bluffed back shoreline, very narrow. And now it's a few hundred meters wide, and it's because there's been waves of sediment coming out of the Klamath River in the last 150 years and basically parking in Gold Bluffs Beach. And so all this landscape is new. It's brand new landscape in the last 150 years. Kind of interesting. Again, that comes from satellites. We tracked that from the last 40 years from satellites. That led us to some of the historical data and allowed us to tell this pretty interesting story. So that's satellites. One of the other things we do is we use airplanes and drones to take photos of the coast and use those data to map changes. And so here's an example of one of our camera systems. That's my colleague Jerry Hatcher. That's a camera that goes inside of the airplane. That's Bob Van Wagenen. Some of you know Bob. He's a local pilot and a marine biologist. He studied phycology back at Moss Landing way back when. And he flies along, we have him fly along the Central Coast and the Santa Barbara coast several times a year to collect photos like the ones you see on the right-hand side, and we use those to document change. One thing, you have access to all the photos, and so every time we fly, we pull those photos. They're put on this data distribution service. That QR code right there is access to thousands and thousands of photos if you're interested. If you don't have a phone, don't want to take a picture of the QR code, email me, jwarrick@usgs.gov, and I can forward you that. And there's some really nice aids that can be uploaded into Google Earth, and you can find photos and see where they're, if you're interested in that. So that's one of the things we do with the photos. We just publish them and make them available to you. The other thing is we use them to build 3D models, 3D representations of the landscape using photogrammetry. It basically, by taking photos from different perspectives, you can reconstruct the three-dimensional patterns in the object that you photograph. And we do that. That's an example of the Santa Barbara coast. Near Rincon and Oil Piers, although the Oil Pier doesn't exist anymore. That's a surfer name, I guess, right? There on the top. So here's an example of one of the point clouds we made for southern Monterey Bay, showing all kinds of interesting processes, erosion processes on the dune face, here's another example. This is Mud Creek landslide. These are data points. This is not a photo. This is a 3D data point. If I had, if you were sitting in my lab, I would open this up. We could spin around and zoom in. This point spacing is about a decimeter, so it's about that. So and it includes color. So each 3D point has RGB color on it. Very similar to what folks are doing in tide pools or up in the landscape to measure changes or quantify species, etc. One of the neat things for Mud Creek is we were out there taking photos before the landslide occurred. And so what I'm showing here is a time series of the evolution and erosion of that landslide feature. And these data, when we started seeing the wholesale melting, I'll call it, of the mountain, we were, of course, in contact with Caltrans and the sanctuary to let them know what we were seeing. And these data helped in the response to that event. And one of the reasons that there were no people or killed or equipment lost is because we knew the magnitude of this event before it happened because of these data. I'll let it play one more time. You can just see that mountain melt away. We continue to monitor that side, of course, because we fly that section of the coast. And so that landslide, it continues to change. And so here are some examples of the changes over last winter. So this goes from the 23 summer to the sort of end of winter in 24. And you can see there, look at the upper portions of the landslide, right? This landscape is still moving, which is part of the reasons why they've engineered the bottom section of the landslide so heavily, is to prevent any potential hazards from this type of movement, but still something to keep our eyes on because it is still moving. One of the neat things that we can also do with this is look at sort of finer scale changes, and so on coastal habitats. And so, for example, here is this is an ortho photo, so it's a mapped image of the coast right adjacent to the landslide the day before the landslide occurred. Okay, so we were fortunate enough to be out there the day before it occurred. You can see that these are massive boulders, very difficult to sort of walk on habitat. And a week after the landslide, you can see the landslide over there on the far side, right? And note that you're starting to see a little sandy beach form on the side of the landslide. And that beach grew, and it grew, right? So what's happening is that landslide, all that new material, waves are attacking it, eroding it, and transporting that sand around the point. So we're starting to see this beach being formed from that new sediment that was introduced, changing the habitat, et cetera, et cetera. Of course, Caltrans comes in and starts rebuilding the road, and so we start seeing construction activities and still the beach there. So if we look through a transect of this, not only do we have these ortho photos, but we have 3D information. So if you're interested in how these habitats changed and how far those changes occurred, I won't step you through all these data, but you can see there, this is a profile looking at the vertical elevation of that of the beach region, and you can see how much change occurred over time from that, both the event and the reconstruction of the road. We've also helped the city of Santa Cruz with the response to the West Cliff Drive erosion that occurred in January of 2023, where we had unbelievably large waves that coincided with very high tides and destroyed a big chunk or several chunks of West Cliff Drive. So this is a before 3D image, so that's all data, 3D data, and this is an after. And I know it's hard to see the changes, but I'll point my finger right there. You can see that the white barrier that's been put up on the road, and you can see how much the holes that were sort of made in the cliff. Here's a change map, and this is probably much more useful than trying to flip between the two. And this change map, we were able to provide this to the city within about 48 hours after the event. And this allowed us and them to evaluate the changes that occurred, both in some areas of riprap that didn't change. You can see the white colors mean no change, and then some extensive erosion, both in areas where there were undercutting of the road, but also a lot of the armoring moved around in areas where we didn't see holes made in the road. So this was a really useful product for them to get information about what had transpired over that big event. So just an example. If you're interested in that data, we've posted it. We actually have a 3D viewer. You can fly around the data. This QR code will take you there. Click on View the Data, I think, and you can just play around with it. And if you have any questions, I'm sure my email's on there somewhere. You can ask me about what those data show. And so lastly, we also get in the field quite a bit. And there's all kinds of neat new technologies to do that too. And occasionally you'll see our folks out in the Monterey Bay. We do have permits, so thanks for checking. we typically there's 2 and a ground support crew. So if you're interested in what they're doing, feel free to talk to the ground support crew, but know that they're also there for safety. If anything goes wrong, they're there to basically help. So if they're not focused on you, please forgive them, and give me a call and we can talk about the data, etc. So these have, we were just talking about sound in the last talk. These have echo sounders that sense how far off the bottom, how far the bottom is from the vessel, and then on top of that, there's a GPS receiver that gets a very accurate measurement of where that boat is. And from that, you can map the seafloor. And so some recent data here are shown here, and this is some work that Amy East in our group just got a paper accepted. So if you're interested in this, I can send you the paper. But showing this is the San Lorenzo River mouth on the northern end of Monterey Bay. There's a historical photo from '82 showing the big bar that was formed after some big floods of that year. And that's all new sediment, sand and gravel that's introduced. And it's important to understand that because our beaches are made up of the sand and gravel that's coming off of the landscape. And so we're trying to understand how much is coming off the landscape and where does it go. And so these, on the bottom, you can see some more recent data from 21, 22, and 23. So the winter of 23, you see that big red blob. That's all the new sediment that came in during that season. And again, there's a brand new paper on this if you're interested, and I can point you toward that. We don't just do this in California. We do these measurements along the East Coast, Gulf Coast, all up and down the West Coast, where there's either a reason or a need for it. One example that was talked about quickly in my introduction was the Elwha River Restoration Project. And so this was one of the largest dam removals in U.S. history, world history, until Klamath occurred, but it still is the largest sediment release from a dam removal ever. And you can see most of the sediment ended up at the sea. The tribal reservation is on the delta, and they were losing land at about 1 meter per year for the last 40 years. And so they not only wanted these dams removed to help the salmon return, but also to stop them losing their land. And you can see how significant, I'm sorry, there's not a scale bar on there. That's about 500 meters of progradation of the furthest extent that the delta grew in January 2015 was about 400, 500 meters. So very substantial changes on the coast, all this new sediment coming in and restoring that estuary, etc. So with that, I hope I impressed upon you that these coastal landscapes are both wonderfully complex, that you need your vitamin C, and that they are ever-changing. And I hopefully inspired you to think about how dynamic these systems can be and are. And with that, I'd like to say thank you. And I have time for questions. Yeah, in the back. Right. Is it even being done? The Coastal Commission still issues permits for certain types of construction, emergency construction and the such. So I think it is still being done in certain places. Obviously, West Cliff Drive in Santa Cruz is an example of a place where the road was reconstructed and new rocks replaced, or they were moved back into place because a lot of those rocks washed down the slope. The effectiveness is a very good question, and it depends upon the site a bit. There are examples on the East Coast where the erosion rate is so high that houses, even if they're protected, right, are falling in the ocean because the beach is basically leaving them behind. We don't have a lot of examples like that with erosion rates of that high out here on the West Coast, but so we don't see a lot of houses standing out in the middle of the ocean. But yeah, I mean, anytime that we build on the sand, there was some great philosopher a long time ago who said something about that. Right? These are really dynamic settings, and to think that they are not moving or they are permanent in any way is potentially folly over the long term. I guess that's one way to answer that. Yeah. Yeah, great question. So Mud Creek landslide. That winter we got a tremendous amount of rain. That was the same winter that Big Sur River flooded, and we had all that sediment come out of that river. And so with landslides, I used to make mud pies. I'm not embarrassed to say, when I was a little kid, and I just right in mud pies, there's a water content where it gets, you add water, and finally it gets goopy, right? And then you can play with it, and then you dry it out, and right. So, think of that mountain in the same way, right? There is a certain level of water content in that matrix, on that rock, that material, right? That things get goopy. They start sliding. Not to give, try not to dive too technical here, right? But those physical properties are based upon that water content. And so for a deep-seated landslide, that landslide occurred in May, right? May, it hadn't rained for months. So why did it wait so long? Does anyone think they know? Why would it occur in May? Why wouldn't that landslide occur January 24th? I don't know, right? The day after the rainfall. Does anyone? Yeah. It's got to percolate down, exactly, right? That the slip plane of that was 10, 15 meters deeper, right, than the ground. And so that rain, that water had to percolate down, right? And then it started to get loose. And it started moving in April. We saw it. And then it started moving more and moving more. And then it started accelerating. Gravity won. The stickiness, lost to the gravity. And gravity just pulled it down. So that's one factor, is rain. The other factor is the rocks out there are just this, we call it a melange, which means it's geologically blended. It's just this crazy assortment of all kinds of materials that sort of have been mixed together, sort of like a really good ice cream, right? And so that is not structurally as sound, or at least it's not as well understood in terms of how structurally sound it will be as maybe sedimentary rock, which is layered. And so we see lots of larger landslides in that material because there are some of these, let's just call them fudge ribbons that are underneath, right? And they can become failure planes. Did that help? Yeah. Yeah.
So, yes, I have another question.
Good.
In the interest of brevity, can you comment about the Cemex plant in Warrick? Jim, have you noticed any effects of its closure? And have you noticed any effects before it was closed? Cemex was having an effect on southern Monterey.
Yes, so the Cemex plant, as you probably know, was the last of the sand mining plants in the Monterey Bay. Historically, there were a bunch of sand mine facilities in southern Monterey mostly, and it closed, and so the idea is that when you're taking sand away, right, it's like your bank account. If you have kids and they're sending them to college, right, you're removing money from your account. The same way, if you're removing sand from the beach, there's a net reduction. And there has been work that showed that with the cement plants, the rate of erosion of those dunes was comparable to the amount that was removed. So the science suggests that, not my work, but others suggest that yes, that rate of erosion in the southern Monterey Bay was comparable to the rate of extraction of the sand. We are going to process a whole bunch of data this summer, and I have a student from CSUMB who's going to help us with that. And we're very excited to look at whether we're starting to see the sort of the opposite effect, either a slowing down of that erosion rate or potentially a stopping. We'll have to see. But I think we have all those aerial photos that we have now since 2016. So we have very high resolution data that can be generated for all of Monterey Bay. We'll be doing that this summer. And the hypothesis is that we should see at least a slowing down of that erosion rate, and potentially a stopping. We'll see. So yeah, we're really looking forward to digging into that data. And I'd love to talk with you longer if you want to hang out. I entertain any questions. I love this stuff. So yes, in the back. That's a great question. So, so the USGS, of course, we're federal. We are a science agency. We don't provide any, we don't manage any lands. We're purely a science agency. So we provide the information and the data for you all to make the decisions, right? So that the decisions of Westcliff are being made by the city of Santa Cruz and the state of California, et cetera. And that is a sort of local, regional, state government decisions, which are informed by our leaders who we elect as citizens, right? And so, so we provide as much information as possible, as much understanding to those as possible. But the rules in our agency is we do not tell you what to do. That I'm making it as simple as possible, but we are not, the USGS does not tell the city of Santa Cruz, build it this way because of whatever. If we can help inform them about various physical processes, et cetera. But you nailed on a really important topic, and that is we live on an eroding coast for the most part. I showed some examples of non-eroding coasts. I showed you Gold Bluffs Beach. That's an exception to the general rule of our coast is eroding. We're on an active geologic margin, and Big Sur, Westcliff Drive, take that and you can go from San Diego County to the Oregon border, and you will see time after again the same types of challenges and problems because we have cliffs that are eroding. Cliffs don't regrow, right? That's kind of a silly thing to say, but it's the truth. And we need to deal with that as a society. And we can, we're very good at engineering solutions, I think, and so I think in some ways, like for example with Highway 1 in Big Sur, it's a question of what we as citizenry want to do and what it's worth to us, because it's an incredibly valuable place for tourism and for getting people out to see nature, but it also costs a lot of money, and that's sort of a society decision in the end. But by all means, that's a coast that's eroding, and we're going to continue to have similar things like Paul's Slide and Mud Creek Slide over in the future. So we just need to be ready for those. If we want to keep Highway 1 open, or if we want to keep Westcliff the way it is, we just need to realize that these things are going to continue to happen and continue to happen and continue to happen and happen more with sea level rise. So, yeah, that's probably not the answer you wanted, but that's the world I live in as a federal scientist. Yeah.
Did you guys do it all with that sinking building in San Francisco?
I didn't know which. Oh no. Tom Parsons worked a little bit on the big. I forget the name of the building. Yeah. Tom Parsons is a colleague, and he actually worked on. It's a great question. On the deformation of soils beneath cities from just the physical weight of all this stuff we've built on it, and it's massive. It's way bigger than sort of engineers had calculated before, and so did we work on it? Not really, but he's worked on that problem in New York and San Francisco and others, and showing that we probably haven't up to now planned for these types of problems in adequate ways, and we need to change the way we've thought about this. Yeah. Yeah.
Does the San Francisco survey have any data on some of the work estimate?
Oh, that's a good one. We haven't done much work in Morro Bay, no, but we would love to. We're kind of strapped with resources in terms of how big we are. But we can always be led by good needs, scientific needs. And so if you know of some, let's talk. Yeah. But I went to Cal Poly SLO, so I really love. I was a soils major down there, so learning about the watersheds and was part of my early education. So, all right, I want to thank you all.